Okay, so it's a great pleasure to have Cindy. This is gonna be high dimensional statistics day one of 6.
Day 1 of 6, yeah. Thanks. Okay, so I guess I'll tell you a little bit about my plan. So the first 2 or 3 lectures, I'm just going to kind of talk about high dimensional statistics generally, kind of set up some, of the kind of formal introduction, the language we use to talk about these problems, and these sorts of things. And then the second half of the course, I'll talk specifically about approximate message passing algorithms, which are kind of a class of algorithms that have been used to study high dimensional problems in a number of ways. So that's kind of the plan. Today, the whole point is to just kind of investigate why we care about high dimensional statistics in the first place. So I guess a few caveats. My handwriting is not great. So someone on Twitter once said it was the second worst handwriting he's ever seen in a lecture. So if you don't if you can't read what I'm writing, it's definitely me. It's not you. Just ask, and I'm gonna try my best. But this is a limitation, Okay, so just to kind of give some introductory kind of notes. Oh man, let's see if I can. Okay, should recognize the pencil now. Okay. So some introductory notes. So kind of the roots of high-dimensional statistics go back at least to, the 1950s. And, I'm thinking about guys like, Rao. Rao is not spelled like that. Rao, Wigner, Kolmogorov. We'll see an example of some sort of high-dimensional asymptotics Kolmogorov gave, Huber, and other folks like this. We're kind of talking about high-dimensional statistics today because there's sort of been a recent surge of interest, I guess. And by recent, I mean maybe in the last 20 to 30 years, especially in the statistics community. More or less because, the modern data sets that we're studying are kind of extremely large. So sort of before computers, what was the data that statisticians were thinking about? It was really kind of designed experiments, right? So, you had drug trials or these, agriculture, right? And they were really designed experiments where, they were kind of considering a few variables, a few covariates, and then, the sample size was growing. But now kind of the data that a lot of statisticians work with is sort of this kind of found data, right? You scrape the internet and collect, kind of everything you can find. So the types of data sets have changed in the sense that now it's not uncommon that you have many variables on each of the individuals in your data set, and perhaps even the number of variables is roughly kind of the same size as the data itself. So just to kind of lay out what do I mean versus classical versus high dimensional statistics. So in short, right, classical is sort of a low-dimensional statistics. And by this, I mean the following. So if I think of, there's kind of 2 parameters that characterize the problems we're thinking about. So we'll take D to be the ambient dimension of the data. Right, and N will be the size of the data, or the number of samples. Right, so if we're thinking about the usual kind of like tabular data set, right? N is going to be the number of like observations, right? These are the individuals. D is going to be the number of variables that we've, we've gathered for each individual. And so then in classical sort of statistics and asymptotics, the idea was you fixed D, right? So D remained fixed. D is fixed. And N grows. Right, so this would be like you have, a growing number of individuals. You're asking questions about, 5 or 6 different aspects of their, their life or whatever. Okay, high-dimensional statistics, right? High-dimensional asymptotics means the following, right? No longer is D going to be fixed, right? But rather, D and N are both growing. So D and N are both growing. And we're thinking of, D is kind of proportional in size to N, or maybe even larger. Right? So, okay, so the question that I want to investigate today is the following. So, what we're going to do today is try to get a sense of the following idea. Let's suppose we have a data set, all data sets are finite sized, right? So we have, let's say, N equals 1,000 samples. From a statistical model. With, let's say, D equals 500 dimensions, and D equals 500 dimensions. Right, so the question is, which asymptotic theory, classical versus high-dimensional, is more useful, right, in kind of describing the finite sample dynamics of this problem? Right, so, okay. So, of course, like the answer to this question depends on like the actual statistical model and these sorts of things, but what I want to do is give just a few kind of classical statistics problems. We'll, look at both sort of asymptotic characterizations and then, kind of experiment with like a finite sample realization and see, what seems to be the better representation. Okay? Okay, so the first example I want to look at is, I only wrote on like half of that. That's okay. Okay, so the first example I want to look at is linear discriminant analysis. So this is like the kind of an early sort of clustering method. So the first example is linear discriminant analysis. Okay, so I'll introduce the problem at some high level. The idea that, it's not so important that you understand, like, all of the aspects of the problem itself. Kind of the important part is to get a sense of what's going on, and then, we want to kind of look at which of the asymptotic theories matches the finite sample performance. So, okay, so the basic idea for linear discriminant analysis is, okay, so this is sometimes called LDA, right, is the following. So let's consider kind of the basic binary hypothesis test. So hypothesis testing is, of course, like, stats 101 level. Like this is, one of the kind of bread and butter tools of statistics. So, okay, so let's consider binary hypothesis testing, where the goal is, right, you have some realization. So I'm going to think of, again, x is some vector in Rd, right? D, again, is the dimension. Where, we want to test, is this drawn from some distribution P1, or is, x drawn from some distribution P2, right? So we're thinking, P1 and P2 represent some PDFs, let's say. Okay, so if, P1 and P2 are known, right, then a natural kind of decision rule is just going to threshold the likelihood ratio, so meaning kind of the ratio of the PDFs. So if P1 and P2 are known, a natural decision rule will threshold the log likelihood ratio. Right, so what do I mean by the log likelihood ratio? I just mean, log of, the PDF of P1 over the PDF of P2, and then, you'll kind of select H1 when this guy is large. Right, so in some sense this says, like, the data seems to be more likely to be drawn from distribution 1 than distribution 2. And, you can kind of formalize, like, why this is a reasonable thing to do. Kind of, one of the big results in statistics is the Neyman-Pearson lemma, which describes the optimality of this test. Right, so in some sense, if you want to reduce, the kinds of errors you make, then this is going to be the like best decision-making process you can use. Okay, so all right, so we're going to think of a kind of a specific case where these P1 and P2 are Gaussian, right? So why are we thinking about this specific case, right? Well, it's going to be easy to analyze if we assume everything's Gaussian. So our special case says, the following, right? Okay, we're going to test between H1 that says, again, our data of dimension D is from a Gaussian with mean mu1 and covariance matrix sigma, against, H2, where, our data is Gaussian with a different mean, and, for simplicity, we'll assume the same covariance, right? Okay, so then if we look at the test statistic, right, this is just going to be the log likelihood ratio that I just kind of mentioned. So our test statistic, we'll call that psi, is mu1 minus mu2 transpose sigma inverse x minus 1/2 mu1 plus mu2. Right, so this is the log likelihood ratio. Right, and it's a test statistic in the sense that if it's large, we're going to say our data is from this guy. If it's small, we say the data is from the second distribution. Okay. Okay, so if we have like no sort of prior information that one of the groupings is more likely than the other, right? So if the sample, if the sample is equally likely, like a priori to come from either, distribution, then, the best thing you can do is threshold this guy at 0, right? This basically just says if the data is more likely from distribution 1, select distribution 1. If not, select distribution 2. So you'll threshold this guy at 0, and then we can characterize the error in this threshold exactly. So the error is in particular 1/2 times the probability that, psi of x1 is less than or equal to 0 plus 1/2 probability under distribution 2, psi of x2 is greater than 0, right? So here, what I'm thinking of, x1 is a random variable from P1, right? This is P1, this is P2. Right, so x2 is a random variable from P2. So then the error, right, this just says like, this is the probability of, rejecting H1 when it's true. And this is the probability of rejecting H2 when it's true. Right, so this says like, you take a sample from actually this distribution, but then, the log likelihood ratio is small. What's the probability of that happening, right? Okay, so this sort of test statistic, what we're doing here is we're kind of like formalizing, what you would think to do in this case, right? So the test statistic just formalizes your sort of natural intuition, right? So the idea is, in one dimension, right, the picture is kind of like the following, you have, it's one dimension, so you might have, this is like P1 Gaussian, this is P2, right? So, mu1, mu2, so this is P2, this is P1. Then the test statistic just says like, if the data falls like on, this side of that blue line, you guess that it's from, this distribution. If it falls on this side of the blue line, you guess it's from this distribution, right? So, if you look at this test statistic, it's literally just saying like which side of the line are we on, right? And you can extend this, in 2 dimensions, 2 dimensions. Now we have kind of, the Gaussian distributions are going to be like, little mountains, right? So maybe if we draw like a kind of like, density regions, I'm not drawing this great, but then, then what we're gonna do again is kind of the test statistic figures out, which kind of center we're closer to. Okay. And so this is a simple example, right? And so, because of Gaussianity, we can characterize the exact, we can characterize this error probability exactly, right? So, these are sort of just, this is Gaussian, right? This is some function, we know exactly what this error is equal to. One can, show that this error is equal to, so this is the Gaussian CDF, -1/2 gamma, where gamma is what? It's the Mahalanobis distance, which is the following. So U1 minus U2, mu1 minus mu2, sigma inverse mu1 minus mu2. Right, so in statistics, so it's basically like the Euclidean distance, but you're kind of like scaling it with the inverse covariance matrix, right? So this is the Mahalanobis distance. This guy, Mahalanobis, was like the father of statistics in India. So he started like the Indian Statistics Institute, which educates like mini-great statisticians these days. And he's kind of a cool dude. Like you should like look at his Wikipedia page. He did like a lot of things in like the government and stuff too in India. That's really nice. Okay. So this is the error probability, right? So this is just the Gaussian CDF, right? And like, it works in like kind of the natural sort of ways. If the means are more spread out, right, the error is smaller, it's easier to classify and these sorts of things. Okay, so in practice, right, we aren't going to know these distributions exactly, right? So in practice, right, if we want to use this as sort of just a clustering technique, right, and this was kind of one of the early sort of clustering techniques, right? You have two groups, you assume they're both from Gaussian distributions, and then if you want to classify a new point, you do this sort of linear discriminant analysis. So in practice, we don't know, in this simple example, it would be like mu1, mu2, and sigma. But instead, we have samples from the two distributions, right? So in particular, I'm going to think of like x1 through xn1 as being IID from Gaussian, my P1. So this is normal mu1 sigma. And then I have xn1 plus 1 through xn2 as being IID normal mu2 sigma, right? And, what we want to do, right, is kind of use these samples to estimate these values, and then, with the estimated values, kind of construct the test statistic and this sort of thing, right? Okay, so, simple idea, right, is we're just going to estimate all of these guys, mu1, mu2, sigma, and just plug it into the test statistic we were looking at before. Right, so we're going to estimate mu1 hat, mu2 hat, sigma hat, and plug into our test statistic psi. Okay, so then what does that give us, right? So I'll call this psi hat of x just to indicate that it's estimated, right? And so now it's just like we write the same thing we had before, but everybody gets a little hat, right, to indicate that they've been approximated from the data. Right, where, okay, what are the natural kind of approximations here, right? Well, it's kind of like as you would expect, right? We can think of mu1 hat as just the sample average of, our first, our samples from group 1, right? Mu2 hat is going to be, the same, but the samples from the other data points. And then since we've assumed a common covariance matrix, we just kind of pool to estimate the covariance, right? So this is like n1 minus 1, sum I equals 1 to n1, xi minus mu I. Uh-oh, I'm not going to have room. Okay. So, not mu, we don't know. Well, yeah, I can write it as mu. So, okay, xi minus mu1 hat, xi minus mu1 hat transpose, plus 1 over n2 minus 1, sum I equals n1 plus 1 to n2. Right, so this is just like, sample mean, sample covariance, nothing smart here. All right, so, okay, so now we have an actual, statistical procedure, right? We use the data, we have a test statistic. And again, because our data is nice and Gaussian, we can kind of analyze the error and these sorts of things. So, if the two classes are equally likely to occur, right? We have no sort of, in this case, it would, well, if we have no sort of prior information on one class being more likely than the other, then what do? We threshold at 0, and we can characterize the error probability as before. Equally likely of occurring. Then what is the error? So the error of our estimated test statistic is going to be 1/2 P1. Now we just, put a hat on it. And again, right, this is the probability of thinking the data came from the second distribution when, it actually came from the first, and then we add the error, the other error as well. Okay, so, the thing that's changed now, right, is that when we look at this error, this is actually a random variable, right, because, this psi hat was constructed from our sample, right, and we're actually only averaging over, these x's. So now the kind of difference here is that this is a random variable because of the data. Okay. So it turns out that Kolmogorov actually, in the 1960s, analyzed the asymptotics of this error, the high-dimensional asymptotics of this error, in like the simple case where we assume that our covariance matrix is the identity. So this is what we're going to look at. Is Kolmogorov's kind of high-dimensional study of this object. So, okay, so in the 1960s, Kolmogorov analyzed this error, assuming identity covariance. Right, so assuming that sigma equals the identity, well, let's say the following. So then the test statistic becomes the following, right? So now we have a sigma hat identity, looking at a new point X to classify. We look at what? So mu1 hat minus mu2 hat transpose X minus 1/2 mu1 hat plus mu2 hat. Again, this is just the log likelihood ratio with the estimates plugged in. So, okay, so he analyzed this guy under high dimensional asymptotics. For the triple N1, N2, D, right? So our dimensions here are the size of our two data sets, and the dimension of the Gaussian sample. And so what are the asymptotics, right? Where asymptotics are the following. So all of them go to infinity. So N1, N2, and D are all growing with kind of these undersampling ratios going to some constants that we'll call alpha. So to make our lives easier, we'll just look at these two ratios converging to the same alpha, right? So alpha, so we have a constant alpha greater than 0, right? And we'll say that, since we're thinking of all these things as growing, we'll say that the distance between, the means is converging as well, let's say to some gamma that's, constant and greater than 0. Okay, so these are the high dimensional asymptotics he looked at, right? And what he showed is the following, that the error of, this test statistic using the identity matrix, or under the assumption of identity covariance, converges in probability to, this is the Gaussian CDF again, gamma squared over 2 square root gamma squared plus alpha. Right, and I mean, okay, he showed something a little bit more general, right? He allowed kind of an alpha 1 and an alpha 2 and analyzed the asymptotics, but we'll just look at this simple case. Right. And, okay, the thing that we want to notice, right, is that this error is strictly larger than the classical asymptotic error. Then the error from classical, meaning like i.e. low dimensional asymptotics. Right, so the low dimensional asymptotics, what do we mean? We mean alpha equals 0, right? Because if alpha equals 0, this just means that, n is, d is fixed and n is going to infinity, so, these guys go to 0. And so what is this, right? This is just going to be the error. It says it converges in probability to, just the error we looked at earlier if we knew the distributions exactly, right? So this is, error as if we knew P1 and P2 exactly. right, so this is what we said, you know, kind of over here. This is the error we're looking at. Okay. Okay, so the question we want to ask, so the question we're interested in, right? Our question is, if we have a finite size problem, which of these error predictions, you know, matches the reality of the finite sample problem? So what I simulated, right, is the following. So for a finite triple, so I'm going to take the dimension to be 400, and N1 and N2 to be the same thing, 800. Right, so this says that the, you know, N is double the size of the dimension, right? So this is alpha equals 1/2, right? And the question is, which error, you know, Gaussian CDF of negative gamma squared over 2 gamma squared plus alpha, or, you know, classical asymptotics, negative gamma over 2, describes the finite situation better. Right, and I guess, like, you know, it's not like immediately obvious, right? I mean, you know, even though, you know, this kind of implies an alpha equals 1/2, right? You know, we're not in this asymptotic land. You still might think that there's something that can be gained from kind of the n equals infinity sort of asymptotic statement, but it turns out that this is, you know, not the case at all. So I simulated sort of 2 examples. So this is a plot of one, so I'll kind of describe what's happening here. So in this plot, right, it's the triple here, right? These are kind of the dimensions, and, you know, I'm letting gamma change, right? So what am I doing? So, okay, so in the plot, sorry, this is not the plot I want. That's why it didn't make sense to me. This is the plot I want. Okay. All right, so in the plot, I'm taking our triple that we looked at earlier. So, you know, D equals 400, N1 equals 800, N2 equals 800. And gamma, right, this is the distance between the means. Is, you know, taking some value between 1 and 2. And then what have I plotted? So the solid curves are, you know, the classic asymptotic predictions versus the high dimensional asymptotic. So this black curve here is, you know, classic asymptotics. So this is the classic asymptotic prediction. Right, the red curve is, you know, high dim. So red curve is the high dimensional asymptotic prediction. Right, and then the blue points are empirical. You know, this is the finite sample simulations. So these are the empirical errors. Right, with you know, the pluses are kind of 3 standard deviations in my trials. right? So, what this says is, like, even though this is a finite sample problem, you're overconfident if you use the classic asymptotics to estimate how well you're performing, right? So, even in, a situation where n is still much larger than the dimension, this high dimensional asymptotics matches the finite sample performance almost exactly, right? And you would be, overconfident in your estimate if you use the classical asymptotics. And I have one more plot where here I kind of I varied alpha, right? So I varied kind of the magnitude of the high dimensionality, let's say. And it looks like this, right? So here, what did I do? Okay, so in this plot, right, we have alpha is in 0, 1, right? So like alpha equals 0 is low dimensions. Alpha equals 1, is you've doubled the size, right? So this, goes from classical to, n is equal to d, right? The data matrix is completely square. I took our distance to be 3 between the means, and d equals 400. So, n equals alpha over d is going to change, right? But again, even, even at this first point I plotted is like alpha equals 0.05. So this is like alpha equals 0.05, right? So we're only like a little bit high dimensional, but it's already like the classic kind of, again, so again, the black curve is classic prediction, right? It doesn't match at all, and our empirics match the empirical, or our empirics match the high dimensional predictions. Right. Okay. Right, so at least in this example, right, what this is suggesting is that, when we investigate, finite sample problems, kind of the classical asymptotics are going to sort of dramatically, mislead you if you try to use them to predict the finite sample performance. Okay, so maybe I'll look at one or two other examples where we're misled by kind of classic asymptotics. So, okay, so another example where, we kind of see our classic asymptotics severely underperforming is something like covariance matrix estimation. Okay, so in covariance matrix estimation, the problem is sort of the following, right? So I'm going to have some data x1 through xn that's IID from some distribution px. I'll assume that, the mean of the data is 0, and again, our data lives in dimension d, right? Okay, so then our goal, if we're doing covariance matrix estimation, is of course just to estimate the covariance matrix, right? We want to estimate sigma equals the covariance of xi, right? And a natural way to do this is, of course, to just use the sample covariance. Okay, so a natural estimator in this case is, the sample covariance matrix, sigma hat equals 1 over n, sum of our data, xi transpose, right? Which is, this is a d by d matrix. So, you know, the first thing we should notice is, you know, this guy is unbiased. So if we look at, you know, the expectation of sigma hat, it's going to equal sigma. It's unbiased. Okay, so what we want to do is, again, kind of think about classic asymptotics for, you know, kind of analysis of the performance of this estimator versus, you know, what we would get if we like look at the high dimensional asymptotics here. Okay, so the classical asymptotics are straightforward, right? You know, you basically just use like law of large numbers to convince yourself that this guy is going to be consistent in kind of any matrix norm you look at, right? So our classical analysis says, you know, what does our classical analysis say? So this is, you know, let's take D fixed, and we get more and more samples, right? And, you know, what you can convince yourself of is that, you know, regardless of the matrix norm considered, sigma hat is a consistent estimator of sigma, right? So, you know, for example, under, you know, mild moment conditions on the underlying distribution the data is drawn from. So under mild moment conditions, can use, you know, classic asymptotic analysis, the law of large numbers, right, to argue, you know, for example, that like let's look at the L2 operator norm, right, of sigma hat minus sigma. This is, of course, just soup. Vector is not equal to 0. Sigma hat minus sigma u 2 norm, u 2 norm, right? You can convince yourself that this converges to 0 almost surely, right? So in statistical language, right, we would say that the sample covariance is strongly consistent, right, where the strong just means almost sure convergence. Okay, so that's the classical analysis, right? Like life is good, the sample covariance matrix works, right? Okay, so if we look at high dimensional analysis, right, this says, how does this estimator work if the dimension of our data is also growing as well? Right, so in this case, we're going to consider a sequence, sigma hat, sigma, right, that kind of is parameterized by n and d with, you know, n and d both growing. And we'll look at this kind of same proportional asymptotic regime, right, where d over n, you know, equals alpha or converges to alpha, some value in 0, 1. Right. Okay, so to study the high dimensional analysis, let's consider, again, just a simple example using the identity matrix. So let's consider a simple example where, you know, the like true underlying, you know, population covariance. We're going to assume this is the identity, and then we're going to study the, you know, the properties of the sample covariance under this assumption, right? So I'll let xi then be iid, Gaussian with mean 0 and, you know, identity covariance where I equals 1 up to n. Okay, so you know, to study the properties of the sample covariance, what I want to do is study the eigenvalues of the sample covariance matrix, right? So we'll study the eigenvalues of sigma hat, right? So the first thing we should notice is that, okay, so the first point is, you know, notice that all d eigenvalues of, you know, sigma equals the identity are equal to 1. Okay, so classic asymptotics, right? We know that sigma hat is consistent. Sigma hat is converging to sigma. So, you know, what this would suggest is that the eigenvalues of sigma hat should all also be, you know, all roughly equal to 1. Right? Let me put that. Okay. On the other hand, right, so when d over n goes to alpha in 0, 1, we can characterize the asymptotic distribution of the eigenvalues of the sample covariance, right? So asymptotic distribution of, you know, the eigenvalues of the sample covariance matrix is given by you guys do random networks. What's the distribution of the eigenvalues of the sample covariance matrix and the high dimensional asymptotics? Does anybody know? No. Okay. It's given by the Marchenko-Pasteur law. Okay. Right, so this is just some distribution, right? But this, you know, this says that, you know, if we take this sample covariance, right, where you know, the true underlying covariance is the identity, then, you know, the eigenvalues will be drawn from this distribution, right? Okay, and so then our question, of course, right, is if we look at a finite size problem, which of these asymptotic predictions represents the truth better, right? So if I have an actual covariance matrix that comes from Gaussian data, right, do the eigenvalues look like, you know, they're all equal to 1, which the classic asymptotics predicts, or are the eigenvalues going to look like they're drawn from this Marchenko-Pasteur law, right? So our question is for, you know, finite size problems, do the eigenvalues of the sample covariance look more like the classical asymptotic predictions right? The classical asymptotic prediction says, like, you know, sample covariance is supposed to look like the true covariance, so this should be a lot of 1s, right? I.e. all 1s, or the high dimensional asymptotics. Right, where high-dimensional asymptotics are described by the Marchenko-Pasteur. Right, and you know, because I'm giving this example, the answer is going to be, right, that they look like the Marchenko-Pasteur distribution. So let me get my plots. Okay, so I just looked at two examples, right? So here, okay, so what do I have here? So in this plot, yeah, you guys can see it. Okay, so this is actually the second one. So this is, I'm taking my finite sample dimensions to be, you know, 4,000 and 2,000, right? So this is alpha equals 0.5, right? And what I've plotted is, you know, plotted eigenvals of the sample covariance, right? So this is the blue histogram, right? There's going to be D eigenvalues, so there's 2,000 eigenvalues, right? And then in red, you know, is the density for the Marchenko-Pasteur, right? So red is Marchenko, right? So you can kind of see the red like here. All right, this is the density of Marchenko-Pasteur. Right, so our classic asymptotics, if this is like, you know, going to be a consistent estimator of the identity, right, the distribute, you know, that's the covariance from which it's drawn, right, this would be a spike at 1, right, but it's clearly like pretty well dispersed around 1, right? Yeah. Well, alpha was less than 1 in the previous example as well, right? Yeah. I mean, in all cases, you know, the things are going to change if the dimension's actually bigger than n, right? So here, we still have dimension smaller than n, but, you know, so I'll see, right? So here I was thinking of, yeah, dimension is half of n. Here again, dimension is half of n. But like, okay, so I took here's another example, right? Let's see if I can fit this over here. So this is kind of the same thing, but now the ND that I've chosen here is, you know, 4,800. Right, so this is an even smaller alpha, right? This is closer to, you know, real low dimensional land, right? But it's still clear that, you know, the high dimensional predictions are the ones that like map us better to reality. Right? Okay. So to wrap up, I'll just give one more example. This is kind of like the classic like curse of dimensionality sort of example that basically says that, you know, when you're in high dimensional space, like all of your data points are far apart. So in some sense, like, you know, estimating a real curve or something in the high dimensional space is functionally impossible. Okay, and then, you know, I'll give one more example today, and then tomorrow we'll kind of talk about like why are the low dimensional asymptotics failing, and, you know, what's our hope for getting around this. So, okay, as a final example, I just want to look at non-parametric regression. Okay, so the goal for non-parametric regression is we have some data basically, and we want to fit a function like mapping, you know, input to output. So we want to estimate a function f that for our example we'll just take values on the unit hypercube and RD, right? So unit hypercube and RD, right? And maps to some real output. And so we're thinking about this as mapping like some predictors or covariates, right? There's a lot of ways to kind of, or input or like, you know, more problematically independent random variables, right? There's a lot of ways that statisticians describe these things, right? But this is going to be the input, which we'll call x, right? These are going to be d-dimensional vectors to outcomes, you know, or response, or dependent variables, y and r. Okay, so if we know the joint distribution xy, pxy, what we want then is you know, something like the following. We want to take the, you know, argmin over, you know, measurable functions and look at the expected squared distance between, you know, the function, you know, mapping x into y. So this is called the least squares prediction error. You know, like why are we using like an L2 kind of norm here? I'll talk a little bit about that like in the next class, but in general, like often when we look at kind of loss functions, the L2 is what we use. Okay, so if we knew, you know, the joint distribution of x and y, right, we would want to like kind of minimize this least squares prediction risk, and you know, maybe I'll move this up here so I can fit this all on one page. And it's easy to show, and again we'll do this maybe in the next class. It's easy to show that the f that minimizes this is going to be the following. It's just the what we'll call the regression function, but it's just kind of the function that calculates the conditional expectation of y given x, right? In statistics, this is called the regression function. Right, so, okay, so kind of like the statistics problem is, you know, we of course, we don't know this joint distribution, so we don't know this regression function, but, you know, what we want to do is use some data to approximate this regression function, right? This is like what it's called regression, right? Okay, so, right, the idea is in practice, right, in statistics, you know, don't know this joint distribution, but we have samples, you know, that are IID samples, let's say, from that distribution, xi, yi. I equals 1 to n are IID pxy, right? And again, you know, this guy is like a d-dimensional thing, and this is just a scalar, right? So then our aim is, you know, to find an f hat to minimize the mean square error, which is, you know, the following. So If we average over kind of a new input, we want f hat to be as close as possible to the real regression function. Okay, so kind of the question I want to look at is, for any given dimension D, so for any given dimension D, how many samples in, right? So how many kind of data points here do I need, to approximate this regression function, like, well, I'm being vague, but, how many samples do I need to approximate the regression function well? Okay, so just to make things concrete, I'm going to assume we know the marginal distribution of the x's. So let's assume x is just uniform draws over this kind of unit hypercube in the d-dimensional space, right? So unit draws from the hypercube, so the marginal of x is uniform on the hypercube, right? Okay, so kind of the idea that we're going to sort of use is the following. So, okay, so to generate, and this is a little bit hand wavy, but I think intuitively it makes a lot of sense, right? So if we're going to generate a good estimate f hat of the true kind of regression function based on our data, x1 through xn, we need that a typical vector, so if we think of like a new data point from the unit hypercube, so we call this x new on the unit hypercube, right? In the unit hypercube, a typical vector needs to be as close to at least one of our sample points. Right, so kind of the idea is, if I have, like, I'm thinking about I'm looking in the unit hypercube, I have some curve in the space that I'd like to estimate. I don't know the joint distribution, which would tell me the curve exactly, but I have a sample of kind of points on that curve, right? And so from the sample of points that are on that curve, can I estimate the rest of the curve? And the high level idea, right, is that you can't kind of have any of the space unexplored, like otherwise you're not going to be able to get a good estimate of the curve there, right? So it sort of says if you look at kind of a new random draw, then you need that this new random point is close in some sense to at least one point in your sample so that you can kind of estimate the curve there by looking at the point that's close. Okay, so there's a number of ways that you could kind of, think about what does close mean and these sorts of things. But, one such example might be the following. So formally, we could study a distance like the following. So I'll call this rho infinity nd, which looks at the following. So if we, look at a joint expectation over a new data point and, our our sample, then we might look at, this is the minimum over all the points in the sample of the infinity norm between, the new point and a point in the sample, right? So, this is, what is this, right? This is the maximum distance in any one dimension between the new point and the point in the sample. And then it says, okay, you minimize over all the points in the sample, right? So you take a new point, you find kind of the closest point in the sample in terms of this, like, max distance over the dimensions. Right, so what do we want, right? It's just kind of like the average distance between our new point and that in our sample should be small. Okay. So what we can study is the following question, how many samples do we need, kind of as a function of the dimension, D, to ensure that this distance is small. So to ensure that this rho infinity is less than some, threshold that we'll call delta. Right? And so, okay, so in the plots, I chose, so I chose delta equals 1/3, right? And so this says that, this isn't like a terribly stringent choice, right? I mean, any dimension is only between 0 and 1, so this says you need a point, you want your new point to be at least like, less than 1/3 of the entire space in every dimension from a point in the data set, right? And basically what we can see is that in this sort of, what one can prove, right, is that you essentially need the size of the data to grow exponentially in the dimension in order for this to occur. So, okay, so here's some kind of plots of this scenario. All right, so this is a plot where, okay, so in green, this is 1/3, right? Blue is the empirical estimate of the distance. And then in black, I have like a lower bound that I'll show in a minute. Right, and so, okay, so what are the problem setting, right? So here I've taken alpha equals 1/2 again, right? So this is kind of the alpha we've been looking at before. So n is 2 times the dimension, right? And the dimension's growing from, d is in 0 to 100. But, basically what this shows is, in this plot, sorry, this is the more aggressive plot. I lied about, let me put the other one down. That was the same one I looked at. Okay. This is, I lied, this is the one that chooses alpha equal, whoa. I don't know how to undo that. Let's see. Okay. Let's see if I can get. Move it a little bit more. That's close enough. Okay. 1/3. Okay, I'm just gonna erase this. Okay, yeah, let me make sure I'm looking at this. I think I got this right. Okay, so in this one, sorry, in this plot I chose n d such that, you know, alpha equals 1/2, so n equals 2d. And this one I chose an even more kind of aggressive scaling. I chose, you know, n is equal to d squared. Right? But kind of the idea is, you know, if you look at this 1/3, in both plots, you know, once you're over dimension like 10, right? So here's dimension 10. The distance is greater than 1/3, right? And, you know, once you're over, I don't know, dimension like 30 or so, the distance is 1/2, right? So that means that, you know, you take a new point and in one dimension, right, it's the closest point in your sample is like, you know, half of the space away, right? So there's in some sense no hope in estimating a curve unless you have like an exponential number of data points. So, you know, you can kind of prove this, right, that, you know, in fact, you need exponentially many, you know, exponentially large n, you know, n d, exponential n d, the dimension, for, you know, this distance measure to be less than delta, right? And, you know, when people talk about the curse of dimensionality, this is what they mean, right? It means that if you're looking in high dimensional space, essentially all your data points are far apart. So if you want to kind of, you know, cover the space with a sample, then you're going to need sort of an exponential number of points to do so. So, you know, one can prove, you know, okay, this is homework. One can prove that, you know, if you look at log of this distance measure, it's greater than, you know, log d over 2d plus 1 minus log n to the over d, right, which implies, you know, you need n to be bigger than 1 over delta to the d to ensure that this distance measure is less than delta, right? So this says you need, you know, a really, really big number of data points if you want, you know, to kind of cover the space. And, you know, this problem sort of remains. So even if you formulated this problem, maybe, you know, again, I'm thinking about an experiment, right? So maybe I can think about having deterministic choice of the x's, right? Instead of drawing them randomly from the hypercube, could I, if I can sample in specific places, maybe I can get around this. But I mean, it turns out that that's not the case either, right? So you can, you know, it basically boils down to studying kind of like delta covers of this unit hypercube, but you can convince yourself that, you know, even if you could choose where the points lie, the points of the curve you want to sample, you're still going to need an exponential number in order to get like a, you know, any sort of real coverage of the space there. So, okay, that's kind of all I wanted to say today. I'll mention that, so I stole these examples, all these examples are from Martin Wainwright's textbook. High dimensional something, something, something. Dimensional, yada, yada. I can't remember exactly, but if you Google Martin Wainwright high dimensions, this will come up. And you know, if you want to check out this is just in, you know, chapter 1 or maybe it's even chapter 0, like the introduction or something. But he looks at all of these examples and talks about them, so you can go there if you want to see more. And okay, yeah, so I'll wrap up for today. So tomorrow, maybe I'll talk a little bit more about these examples. So in particular, kind of like, you know, like what's like the problem? What is the real issue that's not allowing us to scale up these kind of classical asymptotic predictions? And then, you know, kind of, you know, what do we like, what do we hope to do to resolve this, right? So we've kind of seen that like now sample covariance is, you know, no longer a consistent estimator of the covariance matrix. Like that sucks, right? Like what do we do? You know, we have a kind of pessimistic view of regression. It seems like there's no hope, but, you know, we'll kind of talk about like what do the folks who study high dimensional statistics do in order to build like algorithms that actually will do these things in the high dimensions. I'm happy to take questions if there are any. If not, we can go to lunch and I'll see you guys on Wednesday.